All right, welcome everybody. It's time to start. And today we have a pleasure to welcome Aissa, who will be speaking on Cosymplectic Groupoids. Aissa, I give you the floor.
Thank you very much, Anton. So today my talk will be about Cosymplectic Groupoids. So let's get started. So this is the outline for my talk. First, I'm going to give few historic notes, and then give motivations. Then I will define cosymplectic manifolds and explain their properties. Next, I will give symplectic groupoids and then explain their infinitesimal counterparts. You can view them as VP groupoids, or also look at the relationship with Spencer operators. Okay, let's get started. Okay, so first, from a geometric perspective, there are two alternative odd-dimensional analogues of symplectic structures. Namely, these are contact structures, but also you have cosymplectic structures. So of course, contact groupoids, they are studied, and we know a lot about contact groupoids. They have been studied a lot in the last decade, but very little is known about cosymplectic groupoids. I would say it's almost unknown. I started working on this with my student, Sam Jiba from University of Dakar a couple of years ago. So this is an opportunity for me to advertise these cosymplectic groupoids. Okay, but first, what is a cosymplectic structure on a smooth manifold? So cosymplectic structures on smooth manifold, they were introduced by Libermann in 1958. And they were studied by André Lichner-Rovix in 1961. So Lichner-Rovix studied the Lie algebra of infinitesimal automorphism of cosymplectic manifolds. In 1989, Claude Albert used cosymplectic manifold in the study of the reduction theory for time-dependent Hamiltonian systems by some symmetric groups. Yes.
Just a technical point. Mm-hmm. Are you moving through your slides, or are you on the first? Because I see historical notes, right? But yes. we still see the first slide. Is it fine? Is it what how you mean it to be, right? So this
yes.
Okay. So,
but you see well the slide, yes. So yeah.
Yeah, we see the first slide with the title.
So you can see here you have only two pages for this. You can see on the top you can see you have 2 pages.
Yeah, right. But we now on the first slide, right?
Okay, right.
The title page.
That's normal. Okay. You are on the title page. You see the title, or okay, no.
Yeah, we see the title page. Cosymplectic Groupoids.
Oh, really? This is not normal.
Yeah, you see that's why I kind of was worried.
Oh, this is not normal. This is not normal. Let me stop and start again.
Okay.
Do you see my slides now? It's not yes. It's not the title, no? It's not.
No. Now it's the third.
Okay, sorry,
motivations, yeah. 1989, 1995.
Okay. Sorry. So it was some problems. Okay.
Yeah. Now it works well.
Now you see my slides. Okay, good, great.
Right.
Okay, so this was my first slide. Okay. Yes, this was my first slide that I was talking about. Now the second slide. So in 1989, so Ali Shamsuddin used cosymplectic structures as a geometric framework for the study of topological theory of gravity in odd dimensions. So you can see his paper here, which is topological gauge theory of gravity in 5 and all odd dimensions. So this is a paper where he used cosymplectic manifolds. And in 1995, so you see a paper entitled 5 brane membranes and non-perturbative string theory. So here, of course, it's a physics paper, but they use also cosymplectic manifold to study string theory. So recently, there have been many papers where cosymplectic structures appeared in a natural way. So I can say one is the paper by, there are many papers by Eva Miranda and her collaborators on Poisson geometry. And a good reference for cosymplectic geometry is the paper entitled A Survey on Cosymplectic Geometry by Capelletti, Montano, De Nicola, and Udi. So this is a good paper on the subject for those who are interested in this topic. Great. Now, what are my motivations? My motivations, they come from the strong connection from cosymplectic structures, symplectic structures, and contact structures. So because of they're really connected, and contact structures and symplectic structures on Lie groupoids, they were very much studied. So I was wondering, what can we do with cosymplectic Lie groupoids? But to better understand the notion of a cosymplectic Lie groupoids, we first need to start with these cosymplectic structures on manifolds. And this is what I'm gonna go through first. Now, from the viewpoint of G structures, what we call an almost cosymplectic structures on a odd dimensional manifold. So the dimension here is 2n plus 1. This is nothing but the reduction of the structure group from GL and 2n plus 1 to the symplectic group SPNR. Here we take the product with the trivial Lie group. But in terms of tensors, and almost cosymplectic structures on an orientable smooth manifold of dimension 2n plus 1 is given by a pair of forms. So you have omega, which is a 2 form, and you have eta, which is a 1 form. And what we want is that if we take omega to the power n wedge eta, we get a volume form. So from this data, one get the rep vector field. So the rep vector field is the unique vector field, which is determined by these two relation. So if I contract the vector field with eta, I will get 1. And if I contract with omega, this is 0.
Aissa?
Yes.
I have a naive question. How is it? So a contact structure is a particular case. Is it right?
A contact structure is a particular case of an almost cosymplectic.
Mm-hmm. Okay.
Yes. Where the omega is just d eta. But the difference between cosymplectic and contact is that we're going to require eta to be close. Now, and we can't have eta close because for contact because of this relation here, because we want this to be a volume form. Okay, so here we want eta and omega to be both close. If they're close, then we say we have a cosymplectic structure. So almost cosymplectic structures, they include contact structures, but cosymplectic structures, they are not. I mean, contact is not there. Now, another way to define these cosymplectic structures is to look at the hyperplane distribution H, which is given by the kernel of eta. Okay, so this hyperplane would be integrable because eta is closed. And here we want this two form to be pointwise non-degenerate on H. So this is another way to look at it. Now, if you have a cosymplectic manifold, meaning a manifold equipped with a cosymplectic structure, then we have an isomorphism of C infinity modules, okay, taking vector fields to one forms. And if I have any function, so this is called the flat map. Now, this flat map is an isomorphism. So flat inverse of df minus, here I take R when I contract with df times eta, then I get the Hamiltonian vector field. But careful, not all not all odd dimensional manifold can admit a cosymplectic structure. For example, if I take the sphere S2n plus 1, it has no cosymplectic structure. So another way to define cosymplectic structure is to look at the line bundle approach. So then we can define it as what is known as a tier 2 form. So precisely, if I look at the first jet bundle of the trivial line bundle, so then we have this splitting as T star M plus R. And its dual is nothing but the Atiyah algebroid. Now, if I take sections of this bundle, so this is just direct sum of K forms and K minus 1 forms. So in particular for K equal 2, this is what we need. So we'll have a 2 form and 1 form. So this cosymplectic structure is completely determined by a closed Atiyah 2 form. So by Atiyah 2 form, I mean just sections of this vector bundle. Okay, so for 2 forms, so we have just, I call it here omega hat, we have a 2 form and we have a 1 form. So now the relationship between symplectic and cosymplectic structures, of course, is really they're related. They are strongly related. The relationship is very strong. So if I start with a symplectic manifold, I call it M tilde with omega tilde, and I look at the product M, which is M tilde cross R, then there is a cosymplectic structure on M, which is given by omega, which is just the so P R1 is just the projection. So they will push the pullback of omega tilde, get omega, and then eta here is just d tau, where tau is a coordinate function on R. So any symplectic gives a cosymplectic. Conversely, any cosymplectic manifold induces a symplectic structure on M cross R. Okay, so we have here this 2 form omega, which is a symplectic 2 form on M cross R. So this will be called the symplectization of our cosymplectic structure. Now we have even a better way to understand these cosymplectic structures through what we call the mapping tools. So if I start with a symplectic structure, and I have a symplectomorphism between, I have a symplectomorphism that I call phi tilde. So my M here is just the cross product of my symplectic manifold with R. And then I will call phi the map, which is given in this form. So phi of xt is phi tilde of x. In this component here, I take t plus 1. Now I take the infinite cycle group, which is generated by this phi. And then I take the quotient. The quotient would be called M sub phi. This M sub phi is a smooth manifold of a dimension, the dimension of M. Yeah, and my omega tilde will induce a 2 form on omega phi. In fact, my M phi is just a fiber bundle over the sphere. So we have this notation here. Now we can.
Sorry, by a sphere you mean a circle, right?
Say again.
By a sphere, you said a bundle of a sphere, but here is a sphere of dimension 1, so a circle.
Yes, the circle, exactly. The circle was a circle.
Thank you.
Circle. Thank you. So now my M tilde has a natural cosymplectic structure coming from the omega that is induced by omega tilde. And for eta, we just take the pullback of g theta, where theta is the standard coordinate on the circle. Now, we have a characterization of closed or dimensional manifolds that have a cosymplectic structure. So a theorem by Lee said that if I have a closed odd dimensional manifold, so then it admits a cosymplectic structure if and only if it is a symplectic mapping torus for some symplectomorphism of some symplectic manifold. So basically, cosymplectic structures, they all come from that construction of mapping torus. So this tells you how the relationship between these two is very strong. Now, another important property is that if I start with a cosymplectic structure, then of course, as I said before, we have, I think I said, yeah, we have this C infinity module, which is defined by the flat map. But also, we can decompose the tangent bundle in a very natural way. So if I have a vector field, I can decompose it as a vector field which is parallel to the rep field R. And we have also here XH, which is just a vector field which is in the distribution, in the symplectic distribution. Now with this notation, so I call sharp is just the inverse of the flat map. Then we have a bivector field. And this bivector field has constant rank 2n if my cosymplectic manifold is a 2n plus 1 dimensional manifold. And the red field is always transversal to the symplectic leaf. And the red field also is a Poisson vector field. So in fact, the symplectic leaves are exactly the leaves of this distribution, which is inevitable because eta is closed. Another way to get symplectic manifold, so to tell you that there are many, you can construct many. And one way to construct is the following. So you start with a cosymplectic manifold, and you take a function on your manifold. From this function, you take omega f, which is just omega plus df wedge eta, and you keep the same eta. Then this is a new cosymplectic structure having the same symplectic foliation as the original one. And this red field, you're just taking the red field from the first one and you add the Hamiltonian vector field of f. Now, in particular, if you start with a one parameter family of functions, then you get one parameter family of cosymplectic structures. So this is a way to construct cosymplectic structures on a manifold starting from one. But we will not use it. This is just for remark. Now we're going to get to groupoid because my talk is about cosymplectic groupoids. So now that we understand better what these cosymplectic structures on smooth manifold are, we can look at the groupoids. Now I'm going to use here the usual notations for groupoids. So S will be just the source, T is the target, and epsilon will be just the unit map, I the inverse map, and M is just the multiplication. So sometimes I denote by M, sometimes I take M of GH and I call GH. So depending on the notation.
Sorry, my apologies. So there is a question on the chart from Dima about your previous slide. Dima, do you want to ask it or do you want me to read it?
Okay, let me go back.
Yeah, I think he's asking whether you can replace DF.
Yes.
Dima,
Excuse me. Yes. Yeah. I'm asking this question. I was just wondering because this cosymplecticity is is a local condition on on the one form and the two form. I suppose you could. It will not change if if you replace DF by any closed one form. Is that correct?
So if you replace which one?
Well, the DF. So you have action of functions on your manifold on cosymplectic structures.
Right. If you replace so this one is closed. If you replace by another. Well, the thing is, right. If you instead of having an exact form, you replace by a closed form, right?
So that's correct. So closed one forms act on this, on the space of cosymplectic structures on the manifold.
Yes, because the only condition is you need is that if you take omega f wedge eta, then what you get would be volume form.
Yes.
And if you put here another one, yes, it would be yes.
Okay.
That's true.
Thank you. That's what I wanted to ask.
Okay, so I'm going to skip this. This is the usual notations for a groupoid. And just to fix the notation. Now I will need to, in order to introduce these cosymplectic groupoids, I will need to review what we call multiplicative distribution. So what is a multiplicative distribution on a Lie groupoid? So I'm given a Lie groupoid G with a source and target map, S and T, and I take H to be a smooth constant rank distribution on G. The total, on G, okay, on the space of arrows. then I would say that H is multiplicative if it is a Lie subgroupoid of the tangent Lie groupoid, but with the same base manifold Tm. So this notion of Lie groupoid can be understood in a dual way by looking at multiplicative vector valued vector valued forms. Okay. So what is a vector valued form? First, I need to recall what I mean by a representation. So a representation of a Lie groupoid. Okay, so this is just given by a Lie groupoid morphism. Here I call it phi, that goes from G to GLE. So to any element of G, so I have an isomorphism taking a fiber to a fiber. So, but here this is a fiber over the source of G, and here you have the fiber over the target of G. Okay. So this is the usual notation, just to remind what this means. So from this definition, what I need it for is to define what I mean by multiplicative form. So if I have E, which is a representation on G, so what I call by a multiplicative form is just a form that satisfies this condition here. So if I take M, M is the multiplication on my Lie groupoid. And if I take alpha, so these are just one forms with value in this bundle. Okay, so the pullback of the vector bundle E. So this is the usual notation. So here PR1 is just the pullback. PR1 here is the projection onto the first component of G2, and here projection onto the second component of G2. Now, if I take the pullback, so here taking the pullback by M alpha means just taking the pullback by PR1 of alpha, and here, of course, you have the action of that coming from my representation, and here you have PR2 star alpha. Now, sorry, we have a result which is in the paper by Kreinig, Salazar, and Strichner. There is a mistake. Sorry, here is a mistake in the name. So that tells that if I'm given a representation of the representation I call E, and I take a one form on G with value in T star E, then this one form will define a multiplicative distribution, which is just the kernel of theta. Moreover, any multiplicative distribution arises in this way. So this characterizes completely multiplicative distributions. And this is what we're going to use here for Cosymplectic Lie groupoids. Any questions? Yes.
Sorry, I have a very naive question. So, almost no conditions on theta. So in particular, it doesn't need to be multiplicative.
It must be.
Right, you have a multiplicativity property.
It must be, I forgot, a regular one form, regular multiplicative one form.
Okay,
multiplicative one form. It must be. It must be regular multiplicative one form. It must be. Yeah, thank you.
Can I ask a question, Aissa?
Sure.
about the previous slide.
Yes.
If I recall this correctly, maybe I don't, but aren't these distributions arising this way only those that somehow cover the entire tangent bundle of M or something like that? I have the impression that if you want a very, a completely general distribution, a multiplicative distribution induces the distribution of the units, right? And I think that those arising this way with respect to a representation, if I'm not mistaken, they had some peculiarity of covering of this induced distribution on the base being everything. And if you want to have a more general distribution on the base, you probably want this one form to have values in a two-term representation of the homotopy or something. Or put it differently, in a VB algebra, which is not necessarily a representation, just like given by a representation, something slightly more general than that. But anyway.
So what you are saying is that you want
but isn't
to be the projection.
But this regular word, could it stand for?
Maybe I can come back because I can come back to this because you wanna look at this as what they call Spencer operator. I think I can come back to this.
Okay. Yep.
But what I'm gonna use is so Enrique, so you say the one-to-one correspondence, so you need additional condition on.
Yeah, if memory serves me, and I'm not sure if it does. Yes, there was an additional condition on the distribution.
Okay, maybe you
arising
can ask
this way.
the question later when we look at the Spencer operators. Yeah.
Okay.
So this is related. Your question is related to Spencer operators. So we maybe we would clarify. Okay. Now, if I have a multiplicative distribution, okay, then there is a natural representation on the Lie groupoid of the Lie groupoid, sorry, on some vector bundle over M. So the vector bundle over M that I call LM is just the restriction of this normal bundle, which is taking a tangent bundle of G, and you take the quotient by H. So I'm going to go briefly over this representation. So what you do is you take an element G of your Lie groupoid. You suppose that the source of G is X and the target is Y. Now, if I take the right translation G, so this will induce an isomorphism between the fiber LG, where L is just this normal bundle, and LM, which is the vector bundle over M at its fiber at X. Okay, so in the same way, if I take the left translation, LG, I have an isomorphism between LG and the restriction of LM. So here my LM, the way I put it, is not the same as this one. It must be the same as this one. This is the vector bundle over M, but we take the fiber at Y. So now if I combine these two, I get an isomorphism that will send, okay, now my notations, I have changed my notations, that will send the fiber over X to a fiber over Y. And this satisfies the condition of a representation, meaning that you have linear action. Yeah. So any multiplicative distribution gives me a natural representation of G on my vector bundle Ln. Now, when L is trivializable, we can trivialize L, meaning that there is one form corresponding to H. Then we have also so we can look at the representation coming from one cocycle. So this allows us to have, so in this case where my hyperplane distribution is coorientable, I have a pair. So this pair I call it eta and sigma. So here, if I change my trivialization, then the way this pair will change is this way. So if I have another one, I will have eta prime and sigma prime, where eta prime is just here multiplied by a function, and this function here is t star of, so t is the target map of mu, where mu is some non-vanishing, nowhere vanishing function mu. Okay, and your sigma prime is obtained, is also a multiple of sigma. Now, finally, I'm ready to give what I think is the right definition for Lie groupoid. So by a cosymplectic Lie groupoid. So by a cosymplectic Lie groupoid, I look at it as a pair H omega, where H is just an integral multiplicative distribution that comes with a fixed trivialization, so meaning that eta is given. And with this, I have a multiplicative closed to form omega. And what I want is this omega to be pointwise non-degenerate on H. So as a remark, you see that if I have, from this definition, if I have a cosymplectic structure on G, then I get a triple, so which is omega, eta, and sigma. So omega eta is the cosymplectic structure on G, and eta is a multiplicative function. And if I look at G, so this is just the action groupoid that we get from the action of my the H, the natural action we get from H. So this action groupoid will be a cosymplectic, will be a symplectic manifold, symplectic Lie groupoid, and this will be the symplectization of my cosymplectic Lie groupoid. So here we have to look at this in a natural way. So the representation is, a priori, it's not trivial. Although we have a trivial line bundle associated with this, the representation is not trivial. So as an example, of course, these are very simple example. If I start with, just a cosymplectic manifold. From a cosymplectic manifold, I can get a cosymplectic Lie groupoid. So these are easy examples. And then also, if I have a Lie groupoid, we know that on the cotangent Lie groupoid, we have cosymplectic, on the cotangent Lie groupoid, we have a symplectic structure. So the cotangent groupoid is Lie groupoid. Now, if we take the product with R, so here, of course, the action would be, we can take the trivial action. then here we get the cosymplectic groupoid on this product. So the H would be just the cotangent bundle of my Lie group. Yeah, so these are some simple examples. Now, what we want is, from our definition of cosymplectic Lie groupoids, we want to know what are the infinitesimal counterparts of these cosymplectic Lie groupoids. Now, in order to understand this infinitesimal counterparts, we need first to review some construction of Lie algebroids on the first jet bundle. So here I will consider the first jet bundle of a trivial line bundle. So remember that we said that here we want this to be trivialized. So we have here to look at the trivial line bundle, but the action is not apparently trivial. So starting with a Poisson structure on a manifold M. So we know that the cotangent bundle is has the structure of a Lie algebroid. Now also we know that if we take the line bundle, the trivial line bundle, if I want Lie algebroid structure which are compatible with the cotangent Lie algebroid here, so I need to take just vector fields that are Poisson vector fields. So with this, if I start with a Poisson vector field, then I can get a Lie algebroid structure on the first jet bundle, okay, which is defined this way. So it's such that the tangent bundle is a subalgebroid. The line bundle is a subalgebroid, and you have to compatibility. So this is the natural construction of how do you call it? So we have a bi-cross product of Lie algebra, but this one is very simple. So we're going to use this. But let me remind that up to a Lie algebroid isomorphism, so this Lie algebroid structure on the first jet bundle is independent of the choice of the representative that we choose in the first cohomology class of E. Okay, so if I choose another representative, so this new representative has the form, it will be E plus Hamiltonian vector field, and the Hamiltonian vector field of H, for example, if I put H, and from H we can get an isomorphism of Lie algebroids. So the isomorphism is defined this way. So it will send this algebroid to this one corresponding to H. Now we get the theorem. So this is theorem with my student from University of Cheikh Anta Diop, Dakar, Sem Jiba. So we see that if I start with a cosymplectic Lie groupoids, so we only prove in a simple case, but can generalize. So if I start with a cosymplectic Lie algebroid, if I start with a cosymplectic Lie groupoids G, and I look at the base manifold, so there is a unique Poisson structure on the base manifold such that the target map is a Poisson map, but also it comes with a Poisson groupoid, a Poisson group cohomology, okay? An element of the first Poisson cohomology group. So we have two things that we get from the cosymplectic. Of course, we have Poisson, but also we have a Poisson cohomology group. So conversely, if I start with Poisson manifold, and the class of a Poisson vector field. Then I can construct, of course, a Lie algebroid, this Lie algebroid that we constructed before. And if this Lie algebroid is enumerable, then the associated source simply connected Lie groupoid will be cosymplectic. So the one-to-one correspondence between contact in Poisson, contact in Jacobi manifold or symplectic in Poisson manifold. So this is extended here. So here we have cosymplectic, we have Poisson, of course, but with an additional data, which is quite reasonable because every cosymplectic manifold is a Poisson manifold, but with some additional data. Any questions? Okay, now we're going to give the brief sketch of the proof. Of course, if we start with a cosymplectic Lie groupoid over M, then we can take the Poisson tensor on the base manifold as just taking the push forward of your Poisson tensor from your groupoid. And the vector field A is just the push forward of your rep vector field. Conversely, if we start with the Poisson manifold with a Poisson vector field, then we can construct our Lie algebroid. And if this Lie algebroid is enumerable, actually it would be enumerable if and only if so the Lie algebroid obtained by using, so here, of course, I forgot to mention that because E is a vector, Poisson vector field, so E also will be one cocycle for this Lie algebroid. Will be one cocycle for this Lie algebroid. Okay. So, and here we can construct an M cos R. Here we can construct a Poisson structure, and this Poisson structure will be enumerable if and only if G1 is enumerable. Okay, so now if we assume that the first state bundle is enumerable, and we denote by CG the source simply connected Lie groupoid integrating the first state bundle. So we are here, of course, I need the fact that E is the algebraic cocycle. So this will integrate into multiplicative function on this Lie groupoid. And this is where we get the other data from the action actually. And what we obtain is that the source simply connected Lie groupoid corresponding to the Poisson structure in here. So of course, this would integrate the cotangent bundle of M cross R. And these two will be isomorphic as Lie groupoid. So we use some type of Poissonization because from my Poisson structure pi and E, I can obtain a Poisson structure on M cross R. And inequality for this Poisson structure is the same as inequality for this Lie algebroid. So we use some type of Poissonization here. Okay, now the relationship with VB algebroid. If I have a cosymplectic groupoid, and I call the normal line bundle L, then we have a VB groupoid. But the core of this VB groupoid is just trivial. So this is opposite to when we have a contact Lie algebroid. Then the core is a real line on them. So you can see the difference. It's really not the same. But here my L is canonically isomorphic to the action groupoid induced by the action of G on R. Okay. So I can look at it as T star of this Rm. Now I need, in order to explain how you can view, how we can prove the one-to-one correspondence between cosymplectic groupoids and their infinitesimal counterparts in terms of Atiyah algebra. So I need to define what I mean by multiplicative Atiyah two form. So remember that the Atiyah two form is composed by a pair of two form, differential two form, and a one form. So I can view it as a map that takes element of this fiber product and send it to R pointwise. Okay, and as a map, so we know what it means for this map to be multiplicative, and we can define that the multiplicativity of omega hat is the same as the multiplicativity for this function. Okay, now with this definition, we have the following. Of course, this works only when the action coming from H is trivial. Okay, so when the action coming from H is trivial, then the multiplicativity of the cosymplectic structure is the same as the multiplicativity of this omega hat. Okay, and from this omega hat, we get, so you have two tensors, you get two tensors on M. You have a Poisson tensor, and then you have a Poisson vector field. So I did not want to give the proof using this framework of Atiyah two form, but you can do it provided that you stay in the class of cosymplectic groupoids having a trivial action. The same proof that we did, you can also do it using this language. Any questions? Okay, so let's move. Okay, now in my definition of cosymplectic groupoids, I need integrable multiplicative distribution. Now, this integrability condition is important. Now, this type of object, they were described in a paper by Kreinig, Salazar, and Streshina. So here I write the correct name. So they characterize them using their symbol representation. So let me briefly remind what this means. So if I start with a multiplicative distribution on G, and I look at, I call here H sub S, as the intersection of H and the kernel of DS. So this has constant rank. So I have a well-defined vector bundle, which is a subbundle of the kernel. I mean, I have to take the restriction to M. Okay, so if I take the restriction to M, I have a subbundle of just the Lie algebraic of G. And this subbundle is what they call the symbol bundle of H. Now, coming back to what Enrique, you were saying. So I guess it must be this map here. Is that correct or no, Enrique? So L here.
So I think that my confusion, I think Luca Vitagliano pointed it out to me. I think my confusion came from the fact that I believe in your definition of multiplicative distribution, you assumed something about this induced distribution on the base as being the whole tangent bundle. This was part of your definition. So the result is just that, in general, a general multiplicative distribution, may not have this condition. But if this is included in your definition, then it's fine.
Okay.
Yeah, then everything makes sense. Yeah.
Thank you. I will. Thank you. So here we have a canonical projection. Of course, this projection is subjective. So what they get this characterization. So here I use involutive, which is the same as inegable. Okay, just because they use involutive, which is the same as inegable. So there is a one-to-one correspondence between involutive multiplicative distribution H on G and pairs E and nabla E. So E is a vector bundle and nabla E is a flat E connection. And it comes with a parallel nabla parallel tensor, which is exactly defined using this connection nabla with L. So the L that I had before, which is the projection, which is this projection onto the quotient. Okay, so this gives us a description for the eta that I have in my definition of cosymplectic structure on a Lie groupoid. So, but we have another data which is missing. Actually, I come back and explain what do I have from their characterization here. Of course, my E is the trivial line bundle. And also, what is this flat connection that they have? This flat connection can be interpreted as just a Lie algebraic cocycle, okay, which integrates into a multiplicative function, okay? And this field will induce a representation of A on the trivial line bundle. Okay, so the first piece of data is here. Now the second piece in the definition of a cosymplectic Lie groupoid is this multiplicative closed-to form. And it can be viewed as a two-Spence operator. Okay, for those who know what Spence operator is, I think we know what I'm talking about, but I would remind here what it means. So, but this definition is more restrictive than what they have in the paper, because here I will restrict myself to scalar valued Spence operator, because my vector bundle is just the trivial line bundle. So their definition would be equivalent to this one. I mean, we restricted definition. So I start with a Lie algebroid of a groupoid with anchor row. Okay, what does it mean that I have a scalar valued K spans operator on A? So this means I have a pair D and L, where D is just a first order differential operator on A, with value in omega K of M. And L is a map that sends the Lie algebroid A into this vector bundle. And it satisfies these 4 conditions. So I will go very fast on this because these are just the compatibility conditions between these two. And also the structure of the Lie algebroid. That's why you have a row there. These are natural properties. And this definition is equivalent to the notion of an IM form when the representation, I mean, here there is no representation. No, actually it's basically the same here. Okay, now how is it defined? So of course, when I say when the representation is trivial, this means that I suppose that I start with my distribution here, and I have E equal Rm. Okay, then my omega-2 form. So to say that this is multiplicative, when I have a trivial representation, this is same as to say that I have what we call the IM form. So the correspondence is a one-to-one correspondence given by these equations here. So alpha is an element of, is a section of A, and alpha with an arrow here is the corresponding right invariant vector field on my groupoid. Now, our original goal was trying to get extension, I mean, to extend or to generalize Lie's theorem in this setting. It can be done. Of course, I won't have time to explain how. It can be done. I say in the easy way, it's not that easy. You have to work out some details here. But this can be done only when we restrict ourselves to the class of proper. We need our Lie groupoid to be proper. And we want cosymplectic Lie groupoids coming with a trivial representation. Now, in the case where the representation is not trivial, I have no idea how to do that. It's very subtle, it's complicated. I mean, there are some hurdles there. Okay, thank you. I'm going to stop here.
Okay, thanks a lot.
I think I went over time. Sorry about that.
No worries. So please, questions or comments. You can either unmute yourself or raise your electronic hand. I had a very, probably very naive question about somewhere in the middle of the talk when you said that you need, in addition to a 2 form and a 1 form, you also need a function, right? Remember, there was a remark.
Mm-hmm.
But I must say I got lost a little bit at that point. Well, what was that function and how?
So,
then, mm-hmm.
So my H is your multiplicative distribution. Mm-hmm. It naturally comes with an action. Mm-hmm. And from this action, because we are working with line bundles, so this action give us multiplicative, is completely encoded into a multiplicative function on your groupoid.
But then in the examples, right, on the next slide, I don't know whether you want to go to that place, because on the next slide, there were some examples.
Yeah, in this example, I take the example where the action is trivial.
Oh, okay. So then the function.
Yeah, so, yeah, but if you want an example where the action is not trivial, it's given by this. You can just use this theorem. So if I start with a Poisson manifold, okay, with my Poisson vector field, then let me come back here. So the Poisson vector field will be just one cocycle. If you integrate, you get a multiplicative function, and a priori, this multiplicative function is not trivial; it's not zero a priori.
So what would be?
So, but you need a condition that you can construct it, but not explicitly. It's very hard to find explicitly.
But what's the simplest example where that I should think about when I think about it? Is there some really easy example where the function non-trivial?
I don't think there is an easy example. So one way to do it is to okay. Let me come back to my example. I don't think there is an easy example. So to look at integrable Poisson manifolds. Okay. So and then using this, because I can explicitly tell you the formula for this sigma. So starting from E, you can write down the formula for sigma.
And what is it? No, okay. If it's to come.
Okay, I can. Well, yeah, but I can write down from E. I can integrate this. I can integrate E, and get. There is the formula, explicit formula for omega. But I mean, you can construct it, but explicitly to tell what it is not easy. But there is a formula, explicit formula for getting your function, multiplicative function from E.
Well, and as long as you can integrate a scalar one cocycles into the algebroid, there is actually an integral formula.
Yeah, that's what I'm saying. Exactly. That integral formula, you can use it, but you cannot tell what it is.
Well, yeah, okay.
It's constructive, but you cannot tell what this function is explicitly. It's tough to find an example where explicitly you can tell this is the function. Well, I did not try that, but there is explicit formula for a sigma. And a priori it's not zero.
Okay, thank you. Dima?
Oh, I was just wondering, I had one question. So, so what if this line bundle in your story is not necessarily trivial or not trivialized? You consider it?
Well, the reason why we need to trivialize it is that we need an eta.
Well, that's what I was kind of thinking of. I was thinking of this paper that you were referring to of Greining and Salazar and Strushiner. They have a very elegant approach to Jacobi structures and context structures by precisely by not trivializing the line bundle. So that maybe you have you could have a version of cosymplectic structures with omega and eta not being separate from each other, but kind of like part of.
Maybe that would be a new idea of defining. Yeah, that would be. But if you so there might be a new idea for what omega would be. So of course, if you have the line bundle, I don't know what would it be because the reason why we trivialize that line bundle is that you need your eta here. And what is nice is what I did not understand before when I started working with my student on this is that, when you take, because I give you 3 definitions for a cosymplectic manifold. You have one definition where you have eta and omega. You have a second definition where you have the hyperplane distribution. And you have a third definition where you have a tier 2 form. But if you take the first definition, I mean, I think the most elegant way is to take the distribution definition. Because this distribution, if you work on Lie groupoids, it comes with an action.
Okay, well, if you look at this third definition, and you look at this IT2 form, but then on the jet bundle of sections of a non-trivial or not trivialized line bundle.
Oh, yes.
Where that takes you.
Yes. So yes. Yeah, but this, I think what you would get would be just contact. The reason, okay, I don't know.
That's contact structures satisfy very different kind of differential equations than.
What would be the integability condition? The integrable. So you have integrability.
What is it for the IT2?
Contact is not integrable. It's completely not integrable.
I think there is a comment on the chat. Luca,
Yeah, maybe I can comment in person. Hi, Aissa, how are you?
Hi, Luca, how are you?
Fine, thanks. Well, I think that there is an answer to Dima's question, which is the following. Can encode basically what I wrote in the chat. I think that you can encode the cosymplectic structure into, well, in the non-trivial line bundle case, into a 2 form on the gauge algebroid of the line bundle with values in the trivial representation. Well, and something similar happens for contact structures, but in that case, you need a degenerate enclosed form on the gauge algebroid with values in the line bundle itself.
And what would be?
It's not complicated, but it's hard to explain by words in 1 minute.
So
I'll give you references if you want. So let it put it that way.
Contact would be non-degenerate, of course, and it would be closed 2 form at tier 2 form.
So yeah, but from my point of view, so you have the gauge algebroid of a line bundle, non-trivial line bundle. You can either consider forms on this gauge algebroid with values in the line bundle itself, on this gauge algebroid with values in the trivial representation, in the trivial line bundle. In one case you get contact, in the other case you get cosymplectic.
Well, that's actually that makes a lot of sense.
Yeah, that should be, yeah. So yeah,
this is how I understand the 2 structures.
Yeah. So the thing is, yeah, my understanding is, of course, you have the cosymplectic structure, and you have also a representation in the Lie groupoid case. So the cosymplectic structure, if you want to look at the line bundle version, you can take a tier 2 form. But how about your representation? How do you I don't know.
Okay. It sounds like a research project.
Yeah, I mean, one needs to think about it, but it must be possible to define that, but I don't think, Luca, do you know if this is defined somewhere? I don't know.
You mean cosymplectic for non-trivial line bundles?
Yes.
Well, this is outlined in a paper of mine with Ori Judilevich and Alfonso Tortorella on basically G structures on line bundles, essentially.
Okay, so yeah, you already thought about it. Yeah, it's a yeah. You're right. I know your paper about G bundles, so I will look at it carefully. So it must be something that someone can do.
Okay, thanks a lot.
Thank you.
Thank you.
Thank you, Aissa.
Thanks.
Okay. Yeah, if there are no more questions, Aissa, thanks again.
Oh, thanks a lot for the opportunity. Thank you. Bye, everyone.
Yeah, thank you, everybody, for participation. So, and see you next week on Global Poisson. Thank you. Bye-bye.